So now let's look at some textures. So again, texture refers to the cooling. And so one word we use is phaneritic. So phaneritic refers to, whenever you see this prefix phan, it means visible. So you can see the grains. For example, when we talk about the Phanerozoic eon, it's visible life. You can see fossils, right? So phaneritic in this case means you can see mineral grains. They're easy to spot, right? So it's coarse grain, probably formed, well, it formed from slow cooling. So that'd be like a granite, because granites have big crystals in them, and that's why people like having countertops made out of granite, because they have pretty crystals, because you can see the minerals, right? On the other hand, whenever you see A, it means without, right? So without, and then visibility, aphanitic. So this would be something that's fine-grained, like a basalt lava, something that erupted and cooled fast over here. See this, right? Cooled fast. Whereas, remember, the intrusive rocks over here are cooling slow. So a granite or coarse-grained phaneritic rocks would form down in the intrusive realm, whereas the aphanitic rocks would be up here cooling fast in the volcanic realm. And then we have another interesting texture where you can have kind of two things going on, where you'll see I usually call it a two-stage cooling history. Part of the history would be where the rock is, or the magma is cooling, and it's forming minerals in the rock here. So you have some crystals forming in here. But then maybe there was an added input of gas or new magma coming up here from the mantle, and this new magma has heated up this magma chamber, added more gas, and we get eruption of this material. And so this stuff comes out. Now it's a lava flow. But what's interesting about this lava flow has those crystals that formed in the magma chamber, but now they erupted along with the rest of the magma that was still not crystallized. It was that hadn't formed any minerals, right? So that's where we get this word phenocryst over here. So a phenocryst is a visible crystal. So the phenocrysts are the ones that are visible. So in the porphyritic texture, here, this would be the phenocryst. Area here where there's no crystals, we call this the matrix, or the ground mass matrix. And usually I think of the rocks that have this porphyritic texture, sort of like a chocolate chip cookie. So the phenocryst would be the chips, the chocolate chips, and then the dough, the ground mass matrix, right? So that's an example of here's ground mass matrix. That's an example of a two-stage cooling history. And sometimes people just call this rock a porphyry. So here's a good example of a porphyry. In this case, we have potassium feldspar orthoclase crystals. I can tell because they have the 90-degree cleavage here, and they're that salmon pink color. So you got this nice little phenocryst of potassium feldspar. But if you look carefully, these kind of grayish ones in here, and kind of dark gray or to black, those are actually quartz crystals. So this rock has the potassium feldspar and the quartz. So rocks with those minerals are typically felsic in composition. So this is really a rhyolite porphyry, and rhyolite is a felsic volcanic rock. So that's another thing about this one. Even though I see crystals, the fact that I see that ground mass matrix that's fine grain, it tells me that this rock was happily cooling slowly down here, but then it erupted and cooled quickly. So if it came out of a volcanic vent, it must be a volcanic rock. Even though it has these big crystals, we're still going to call this a volcanic rock. So other textures that we'll look at that are part of volcanic rock textures are vesicular texture, which are going to have the gas bubbles, and I'll show you some of the examples. And then the glassy texture like obsidian. And then we mentioned the pyroclastic texture already. So here's another way of looking at it. We're looking at rate of cooling, right? So if it cools very slowly, like in this granite rock or granitic rock, you'll see that you'll have interlocking grains, and pretty much the whole magma crystallized into minerals. So it becomes plutonic. And so that's where we get this phaneritic texture. And then, or if it explodes as a tephra, pyroclastic, that's fast cooling, would have this, in fact, some people call it fragmental. So fragmental. And so this is a little micrograph image, like we're using the microscope, and you can see this kind of curved structure. That's really a glass bubble in the magma that was shattered or broken. So these are called glass shards, very typical of pyroclastic rocks, right? And then here is a glassy obsidian. So obsidian it really has two textural terms. One, it's aphanitic. I don't see any crystals. And two, it's glassy, so it's aphanitic and glassy. Now we're going to combine both the chemical, the composition, and the texture, right? So aphanitic texture or fast cooling, fine-grained rocks are going to be, in terms of their chemistry, if they're mafic, it's going to be a basalt. If it's intermediate, it's an andesite. If it's felsic, it's going to be called a rhyolite, just like the one I was showing you, the porphyry rhyolite that I was showing you there in the previous slide. And then as we look at the slow cooling, the phaneritic, they're going to be coarse grained. So these all had time to cool and solidify down here in the magma chamber, so they're in the intrusive rocks. So here we'd have the gabbro. So gabbro is mafic. Diorite would be equivalent to andesite, but again, it's cooled slowly and solidified at depth. And then granite would be the one that's felsic. You can think of all these phaneritic rocks forming down here in the plutonic realm, whereas these volcanic rocks are going to form up here in the volcanic realm. So in this picture here, we actually see the vesicular texture of a basalt. So this would be mafic, faster cooling vesicular. If the basalt is heavily pitted with these gas bubbles, these vesicles, we have a general name. We call that scoria. So the scoria texture is really this vesicular texture. And then when we look at just a fine-grained basalt, hard to see minerals, it's black, it's going to be mafic, so we call that basalt. But if it cools slowly at depth over here in the magma chamber, we're going to call that gabbro. Then another way we look at it in terms of composition, this table here from your textbook is showing those compositions: felsic, intermediate, mafic, and ultramafic. What's nice about this diagram is that we're looking at rate of cooling here. We got aphanitic and phaneritic, so these would be your volcanic extrusive rocks here. Here is your plutonic intrusive rocks. Now, the other thing about this, it's showing what minerals would be present. So remember earlier I said if you have quartz and potassium feldspar, you're going to have some sort of felsic rock. And that felsic rock, if it's cooled slowly, is going to be granite. If it cools rapidly, it's going to be rhyolite. For the intermediate rocks, you're going to have some pyroxene, certainly a lot of hornblende. Plagioclase feldspar is one of the key components here. Note that we have very little quartz, very little potassium feldspar over here, right? As soon as you start seeing potassium feldspar, the orthoclase, you're going to be in this felsic region here. So that would be our intermediate rocks, diorite or andesite. For the mafic rocks, gabbro or basalt, we're going to see a higher concentration of pyroxene, and you're going to start seeing some of this green olivine, right? Then once we get to the ultramafic rocks that occur in the mantle, you'll see a much higher proportion of olivine in these rocks here, these ultramafic. So remember, peridotite is the rock of the upper mantle, and it is coarse-grained. It is a plutonic rock. But if you were to melt peridotite 100%, you'd make a lava out of that. And remember I said that melting the mantle today only gives us partial melts, anywhere from 2 to 10%. That's because Earth isn't hot enough to entirely melt peridotite. So we only melt part of it to produce the mafic basalt magmas that come out of there. But back in the Archean, more than 2.5 billion years ago, Earth was hot enough, and we could melt this peridotite 100%, and we would make these komatiite. So komatiite is an ultramafic lava. We don't see those anymore today because Earth isn't hot enough. And then this is just showing a little bit about the pyroclastic textures here. In fact, I want to talk a little bit about this tephra here and how we're seeing. So for the tephra size ratings, we have ash, lapilli, and blocks. So remember, this is stuff that's pyroclastic, that blows out of the volcano. So ash is going to be finer than 2 millimeters. So it's fine-grained, volcanic ash. Lapilli is anywhere from 2 millimeters to 64 millimeters. So that's about 3 inches. So from kind of sand size to about 3 inches in diameter. And then the largest pieces are the blocks and bombs. So blocks and bombs are going to be greater than 64 millimeters. And so a block is, let's say there's a piece of country rock that's already solid, and it gets ripped out, piece of the wall rock, and it gets erupted by the volcano, and it's already solid, so it's kind of this blocky nature, and it lands on the ground. That's what we call a block. Although most volcanic projectiles that are coming out are maybe little blobs of magma that's still kind of molten, and when it erupts, it's squishy, and as it's flying through the air, it's aerodynamic, and it gets shaped almost like a football flying through the air, and then it lands on the ground. And usually, one of these ends kind of gets bent, so that would be the bomb. And so, in this case, here's a picture of a volcanic bomb. You can see it has this kind of football shape, and it looks like it hit the ground at this end, and that's why this end kind of bent up. So this is one of these things that got burped out of the volcano, flew, and these bombs can be anywhere from about this size here, and some could be the size of like a Volkswagen Beetle. They can get quite large, and so they're really dangerous here. You want to avoid getting hit by a volcanic bomb. Now, again, this picture is showing the scoria here, a pumice fragment, and then here's some volcanic tuff. One thing about volcanic tuff, a volcanic tuff is a pyroclastic rock composed mostly of ash. All right, well, we'll stop here for now.